In this tutorial, we'll go over Hess's law. So Hess's law helps us to find the enthalpy of a given reaction using the other reactions. Okay, so let's get started. So what we get to do whenever we're working with Hess's law is we look at the overall reaction. So this is the main equation that I want us to find the enthalpy. So you'd want to look at the other reactions, reverse them in the way that they are going to give us that one. Okay, so now I'll start with the first one there. This is my first equation. Okay, now assuming I reverse it, if I make the products to be the reactants, I'm supposed to change what I have there as well. If I get to multiply the entire equation by 2, I'm even supposed to multiply 2 against the enthalpy of the reaction. And then at the end of it all, whatever we're going to do there is going to affect these, and then we'll just add them in the way that they're going to be. Then they're going to give us the enthalpy of what? The reaction given on top. So now, let's start. So if I try to compare the first reaction, I'm able to notice that basically everything that I have is matching up with the main equation. Okay, including oxygen as what? A product. Now, what about if you go to the second reaction? In the second reaction, I can see that this is on the opposite side. And then I can also see that this is also on the opposite side. So this information is enough to reverse the reaction. Okay, so let's reverse it. So if we reverse it, we're going to have NO3 plus NO2 as our reactants, and we'll have a single product. Okay, so whenever you reverse, this is supposed to change the sign. So since it's positive, it's supposed to become negative now in this case. Okay, so that's what we have now. Okay, what do we do? So I can remove this one since we reversed it. So we now try to compare what we have. Is it okay if we consider it from this stage that things are going to be okay? So whatever appears on the reactant side, or let me just say on two opposite sides of the two equations, is supposed to cancel out. So in this case, do we have anything that is common on both sides? So if I check these against the opposite side there, I can see that I have something that is common, right? So I can cancel it out and then see what we are going to have. So this is going to go, and then that is also going to go, which is a good thing because it's not even part of what? It is not part of our overall equation if you check. Is there anything else that can cancel out? So if I check the other side against the opposite side, nothing is common there. Okay, so let's try to combine what we have. It's going to give us the main equation. So I have O3. So this and this are the same, so they are going to give us 2. And then on the product side, there's this, and then there's also oxygen there. So now the question is, if you compare what you have as your final equation, is it matching up with a given equation? Yes, it's matching up. So what you just get to do is add what had remained as your enthalpy for the two reactions. So in this case, we have 10.1 and then negative 48.3. So that is what you're supposed to do. So we'll say 10.1 kilojoules plus negative 48.3 kilojoules. So this is going to give us what? This is going to give us 38, but of course negative 38.2 kilojoules. So this is the enthalpy of the reaction, and this is what we call Hess's law. So I've got 3 more questions. Let's look at the second question. So far what we've talked about, it's the only thing that is there is just making sure that it's kind of a puzzle now. You're just trying to analyze the reaction mechanism that you've been given so that they give you the main equation there. So after giving you the main equation, you then had the enthalpies that are going to remain on the left, which are affected by either the signs or even by the coefficients in case where you multiply. So this is our main equation in this case. So what is the question saying? The question says calculate the change in enthalpy for the reaction of calcium oxide and sulfur trioxide. So is this reaction exothermic or endothermic? So use the following equations and data. So you can pause the video and try it out from the basic concept that we've talked about in the first question. So it's a puzzle, it's kind of a game. So I'll start with the first equation there. So if we look at the first equation, do you have any compound that is common between the two equations with the main one there? So I can see this, it's also part of the main equation. Are they on the same side? Yes, they are on the same side. It's found on both as reactants. By the way, this application doesn't recognize this, so this means it's just telling you a separation between the reactants and the products. Okay, so the first equation is okay the way it is. Okay, we'll leave it the way it is because we have seen one reactant that is matching up. How about the second equation? Is it okay? So is there anything that we can see that is common? So calcium sulfate is a product in this case. It's also a product there. So this one will remain as it is as well. The third one, anything common? So I can see calcium oxide here. It is also part of that main equation. So in this case, it's a product. In that case, it's a reactant. So there is need for us to reverse this equation. So if we reverse it, what are we going to have? We're going to have, we'll start with calcium oxide as a reactant, giving us calcium plus half of oxygen. So remember we said that whenever you reverse an equation, the enthalpy is supposed to change the sign. So since it's a negative, it will become a positive 634.9. So let me even remove it from there so that we know that we've already dealt it away with. So we've remained with all the four equations, we've analyzed them, they are all okay. There's only one that's required to be changed. Oh, by the way, there's one more down there. So the last one, we have hydrogen, oxygen, water. So is there a need for us to reverse it? So this is where now you need to think, because hydrogen and oxygen they are not part of that equation. So how then are you going to know what to do? So the basic idea is to analyze that we know hydrogen and oxygen, water, are not part of the main equation there. So we want them to cancel out. So meaning that they should be in opposition to the other equations. So if you look at the first equation, water is a reactant. So we would want it to be a product in this reaction so that we can cancel it out. So equally, hydrogen is a reactant here. So where is it a product? It's a product in the second equation. So we would want it to cancel out as well. So this water molecule is going to cancel out with the one from the first equation. This hydrogen molecule is going to cancel out with the one from the second equation. Is there anything else that we can cancel out? So this oxygen as well can cancel out with this one there. Anything else that is common on both sides? Okay, so let's start by analysis from the first equation. So what have remained within the first equation? We've remained with SO3. Is it part of the main equation? It is, so we leave it. How about the sulfuric acid? Is it part of the main equation? It's not, so we'd want it to cancel out. So is there any equation that can cancel it out? Where is it? Do we have it anywhere? Yeah, we do have it in the second equation, and it's on the reactant side, so it will be able to cancel out. If we move to the second equation, we have calcium in solid. Then is it part of the main equation? If you analyze the main equation, there is no calcium in solid as a metal, so this one is supposed to cancel out. So where is it a product? So in the last equation, so it will cancel out. Anything else that we feel can cancel out? We've cancelled out all the things that are required. So we try to analyze what we have on the reactant side. So I can only see something remaining in the first equation and the last one. So giving us calcium oxide and SO3. The products were only remaining with calcium sulfates from the second equation. Okay, so calcium SO4. So this is actually matching up with the equation that we have. So how are we going to determine the enthalpy? We get the enthalpy is from these other equations, and that's what Hess's law tells us to do. So from the first equation, it remained the same because we didn't reverse it. The second one, it remained the same, we didn't reverse it. There was no need to do that. The third one, which is this one, it had to change the sign because we reversed it, so it's a positive value. And this one remained the same as well, so minus 285.8. How many equations did we have? We had 4. So this is 1, 2, 3, and 4. So get a calculator there. Negative 132.5 minus 602.5 plus 654.9 minus 285.8. So what value do we have? We have negative 385. So negative 385.9 kilojoules per mole. So this is the enthalpy of that many equation there. Alright, the third one. Find the enthalpy of the reaction of magnesium oxide with hydrogen chloride. So in this case, guys, the concept is the same. So what you can do is just pause the video, try to solve it. Take your time, then come back. Alright. So magnesium oxide reacting with that. So this is our main equation. So all we are doing is comparing these other equations, part of the reaction mechanisms. We compare it with that equation. So I'll start by comparing from the first one. We have magnesium, we have HCl, magnesium chloride as a product, and hydrogen gas. So from these reactants and products, do we have anything that is common? So magnesium chloride is part of that equation as well as HCl. So HCl is a reactant, so even in the first equation it's a reactant. Magnesium chloride is a product, even in this equation it's also a product. So this equation will be maintained the way it is. The second one, we have magnesium solid, we have half oxygen, magnesium oxide. So anything that is common with the main equation, we have magnesium oxide. So in the first equation, it's a reactant. In this equation, it's a product, so we have to reverse it. So this one is supposed to be reversed. So it will be, so this product will become a reactant. So we have magnesium oxide in solid form, giving us magnesium plus half oxygen molecule. So remember we've said that whenever you reverse it, the enthalpy is supposed to change the sign. So since it's a negative, it will become a positive. So 601.6. Okay, so let's even move it there. Okay, how about the last one? We have water, we have hydrogen, and half oxygen. Anything that is part of the main equation? Yes, we do have water in the main equation. Is it a reactant or a product? So it's a product. So even this one, we're supposed to reverse it so that it becomes a product. So if we reverse it, what are we going to have? We have H2 plus half oxygen as reactants. Then water becomes a product. So the moment you reverse it, the sign is supposed to change. So it will become negative 285.8. So let's cancel out now what is, so let us even remove that from there. So we need to cancel out the things that are on both sides as a reactant as well as its product. So let's put stars on the ones that are not part of the main equation. Is hydrogen part of the main equation? This hydrogen. So if you check the main equation, there is no hydrogen there. So this one we don't want it. Do we have oxygen in that equation? There is no oxygen. Do we have water? We do have. Magnesium oxide, we have it? We do have it. Magnesium in solid form? We don't. Half of oxygen? We don't. We got the first equation. Magnesium in solid? We don't have it. HCl, we do have it. Magnesium chloride, we have it. Hydrogen, we don't have it. So let's try to cancel out now these things with stars. Okay, so magnesium solid there. We'll cancel out. Where else is it? It's there. The H2 there is also an H2 here. This half oxygen, where else do we have an half oxygen? It's there. Anything more with a star? That's all. From the first equation, we are remaining with HCl and magnesium. So HCl has the only reactant to HCl. Plus, there is this magnesium oxide in the other equation. Those are the only reactants that we have. The products, I can see water here and magnesium chloride in the first reaction. So magnesium chloride and water. So this is the equation that we have, and it's exactly matching up with the main equation there, and that was our goal. So we can now get the piece of information that we came up with. So in the first one, it was maintained because we didn't reverse it. So it's negative 456.9. This one, we reversed it, so the sign became positive. This one was also reversed, so from positive it became negative. So it's negative 285.8. So get calculator now and punch. We see what we're going to have as our answer. By the way, in the previous question, they had asked us to determine whether it's an endothermic or exothermic reaction. So whenever the answer is negative, we can say that it's an exothermic reaction. When it's positive, enthalpy, it tells you it's an endothermic reaction, meaning that the reactants add more energy than the products. So negative 456.9 plus 601.6 minus 285.8. I'm getting negative 141.1 kilojoules per mole. Right, for question 4, we are told to calculate the enthalpy. Calculate the enthalpy for that reaction. So equally, we're going to apply the same principles that we've applied in our first few questions. So what do we get to do now? So I'll start by looking at the first reaction. So let's try to check whatever we have against the main equation. So this is on the same side. The oxygen is at least there as well, and then that is also matching up. So I don't see any necessity of us reversing that reaction. For now, we can keep it as it is. Let's go to the second one. The second one, if I check this, I can see it's somehow there on the other side. Okay. What else? If I check this, where can we see it? I think we have it there. If I check the oxygen, we have it there as well. So what have you noticed? It's like this one is, everything is like on the opposite sides with the main equation there. So what can we do? The best thing you can do is reverse it for now. Let's try to reverse it. We see what we're going to have. So if we reverse it, we're going to have 3 oxygen plus 2K2O as our reactants, and then we'll have that as our product, 4K O2. So whenever you do that, this is supposed to change the sign, so it will be negative 411.6 kilojoules. So I can remove it there. Okay, now let's go to the last one. If I check this, where can you see it in the main equation? Are they on the same side? So if I check, it's on the opposite side. If I check this, it is on the same side. And then if I check this, it's on the opposite side. So this is now where it becomes tricky, because we've seen that one guy is on the opposite side. Two of course are on the opposite side. This is on the other side. So that is not justification enough, because we've looked at different equations. So what do we get to do in this case? So what we've noticed is, in one of the reactions, we have what? We had oxygen there, 3 oxygen molecules. In the second one that we've reversed, which is already matching up with what we have there. So which implies that it is unnecessary for us to have that oxygen there. So we want to get to a point where we can cancel it. So if we are to cancel it, then this is supposed to remain, so that we use it to cancel. Now, cancelling it is not going to be possible in the way it is now. Why? Because what we've noticed is, there we have half oxygen. Okay, we have half oxygen. But then, what happens in terms of adding what we have then in this case? If you check there, how much of us do we have? We have 4 of them, and there we just have a single one. And then in the other reaction where we can add it, we just have 2. So we would need to have 2 again in the first reaction. So this tells us to say that what we can do at this point is multiply the first one by a 2, double everything by a 2. So this is what you're going to have. We have 2K2. Let me use a different carrier. So I have 2K2, or so when you multiply the half by 2, it is just going to be O2. And then the other side you have 2K. So I said whatever you do to the reaction is supposed to be done to the enthalpy. So the same is going to be done to our enthalpy in this case. Okay. So you are done with your first equation there. We've done something to it. And now let's try to use what we have now to say if it's going to work out. Any things that are necessary that are on opposite sides. So if I check this, is it anywhere else? So it's not there, so we'll not cancel it. How about if I try to check the products? Oxygen, so I can see oxygen there. Can cancel with the other opposite reaction. And then K2O2, can we see it anywhere on the reactants? No, it's not there. And then I'll move to the second reaction. I'll check it against what is on the bottom. So this is nothing. I check what is on the products against this side. Do we have anything that we can cancel out? Anything matching up? They are not matching, so we'll leave it as it is. And then let's try to write what we have. So we'll start first of all. On the reactant side, what do we have? I can see 2KO2 plus this. Are they the same or they are different? So they're different. But at least, okay, so this is matching up with so if I check this now clearly, I can see that this is the same as that. So that will reduce, giving us 2KO2 at this stage, because the 2 there has gone. And then what we just want to remain with is just this. So what do we do now? If you add this and this guy, they'll give you 4. So what I've added is this and this. And then what are we remaining with? So 3 oxygen molecules. Okay. What else do we have on the products? So on the products, we're remaining with that guy plus, which one is it matching with? This one, which will give us a 3. And then what else? We're now remaining with that guy, 2KO2. So this now matches up with the equation that we have as our main equation. So this gives us now power to us to add what we have as the enthalpies to just give us the final enthalpy for our reaction of interest. So that is what we're remaining with. So remaining with positive 411.6 kilojoules plus 2 negative 132.6. So why is this one positive? Is it supposed to be positive or negative? If you check where it's coming from, we had reversed it, not so. We had reversed this reaction and it was positive initially, so this is supposed to be a negative. So we'll add a negative there. And the other one on top, we didn't reverse it, we just multiplied by 2, so that's what we have. So in this case, if you grab your calculator, negative 411.6 plus 2 multiply against negative 132.6. So what I'm getting as my enthalpy for the reaction is negative 676.8 kilojoules. So that is how you use Hess's law to determine the enthalpies for different reactions. So that's it for this video. Thank you very much for watching. I hope you now are able to answer all the different questions that you have on thermochemistry.